So today is the last lesson for the whole course. We're not going to learn any new material. It's about Taylor series of the special cases Maclaurin series. Okay? So we already know the following two series. The one is 1 over 1 minus x. We know that's going to be this, and the radius of convergence is 1. We also know that e to the x is going to be x to the n over n factorial, and this can be any x. So I just write in this form. Of course, when we differentiate or integrate the first power series representation, then we get others. Okay, so for example, when you differentiate the one on top, you get the 1 minus x squared, right? And that is going to be the power series here to start from, it's n times x to the n minus 1. And you can rewrite it again, use it's k plus 1, x to the power k, for example. Okay. And if you integrate it, so natural log of 1 minus 1 or minus x, and that is going to be negative sign, and that should start from 1, 0, yeah, 1, 0. Okay. And then if you want to use another index, it's actually is going to be 1 here, and k x to the power k over k. Okay. So if we will differentiate, you get the 1 over 1 minus x back. Okay, and so on, right? And if you replace x by negative x, you get a 1 over x, 1 plus x. Okay, so on. So those are the then you continue integrate, then you get arctangent x. So, but how about the e to the x? E to the x doesn't matter if you differentiate both sides. You don't get a new one. Okay, because the derivative of e to the x is still e to the x. Okay, but integrate e to the x, still get e to the x. So nothing you can change. Okay, but we can modify like e to the negative x. Then hyperbolic. We get hyperbolic sine x, hyperbolic cosine x. Okay. So if I ask you to find the Taylor power series representation for hyperbolic sine x, right? You don't need to go through the procedure to find the Taylor series first, then make sure that it's convergent to the function. That takes too much time. You don't need to repeat it over and over again. Just like find the derivative, right? At the very beginning, we learned how to use a limit, right, to find the derivative. But later on, we can use the formulas. Okay. All right. Now, so if you view this one as half of e to the x minus e to the negative x, then you can get the power series for representation for hyperbolic sine x. Okay, so I forgot the formula, detailed formula. So let's write down. Formula here. It's minus. Okay. So when you combine them together, only when n is odd, then you get, yeah. So actually, only when n is odd, then it's again non-zero. Okay, so n equals 2k, So this is a k started from 0 to infinity, and n is 2k minus 1, and then you get 2, so it's going to be x to the 2k minus 1, I think, when k equals 1, yeah, k start from 1, then you get 1, yeah, okay. So that's the formula we get, okay, after you combine them two terms. So today, what we're going to learn is about sine, cosine. Okay, I want to find the Taylor series for the sine x. Okay. How can I do that? There are a couple ways to do. One is we can use the very special formula like e to the ix, which is cosine. E to the ix is going to be cosine x plus I sine x. Okay, but of course we're not talking about complex numbers. We cannot use a Taylor expansion for the e function. Okay, to get Taylor expansion for sine and cosine. So we are going to we're going to directly to find the Taylor series for sine x. Okay, by definition, let's hear the question. Find the power series representation for sine x. Okay, so the power series representation in the form Cn times x to the power n. Okay, how do we do that? If the power series exists, right, then Cn must be Cn, the only candidate you're going to have is going to be the only candidate is going to be this. Okay, but then you still have to prove that it's convergent to the function. Okay, it's not necessarily to be, first of all, we don't know the interval convergence. We don't know the interval convergence. We don't know at the very beginning, right? Whether it's convergent to the given function. It's not clear at this moment. So let's find, this is called the Taylor series or Marconi series. Let's find it first. Right? How to find it? Fx is going to be sine x, right? Then you differentiate, you get cosine x. Then you continue to differentiate, you get negative sine x. Okay, change the sign. And the third derivative is going to be negative cosine x. Okay. So can we get the general formula? Right? Can we get a general formula? And then fourth derivative is going to be sine x again. So x is periodical. Okay? And the fifth is going to be cosine x. So clearly, this is a pattern. Okay? So you get, okay, so I can get the general formula when f is 2k. The 2k is all the derivative. Right? So this is an even term. It's always sine x, but there's a coefficient in front of the sign. Could be negative, could be positive. I think this depends on the value of the k. Okay, so that's the formula we get. Okay, when k equals 1, you get negative sine x. Yes, that's matches. Then for the other number, 2k minus 1, and this should be called cosine x. I have to put the integers, right? So when k equals 1, I should be positive. So that means k should be minus 1 here. when k equals 2, you get a negative cos x. Okay, so this is the formulas we have, and then evaluate at the 0 point, it's going to be 0 anyway. This is going to be negative 1 to the power k minus 1. Okay, so now we get the series. Yeah, we do get a series. We get series k. This is supposed to be n start from 0. Okay? Since only when n is r, then it's going to be non-zero. So when k equals 1, okay, only those terms are still there. Okay, when n is even, they're all equal to 0. All right, so now, yeah, now let's rewrite it again. This is going to be negative k minus 1 to k minus 1 factorial x to the 2k minus 1. So the question is whether this is going to be cosine x. We don't know yet. Okay. Whether this is converging to cosine x. We find the candidate. Okay, because if it has power series representation, then that must be this one. The question is whether this one is always convergent, on which interval it's convergent. Right? Whether it's convergent to the cosine x, we don't know yet. Okay. Taylor's contribution is he finds formula to find the formula, the following encoding. We call the Taylor's, yeah. By Taylor's encoding, he found out the difference is sine x. Okay. Should I use sine? And yes. So this is going to be. Let's use. Okay. This difference, right, can be controlled. Now, what is that number? The next number is it's controlled by some n, right? And this is going to be absolute x to so actually the last term is 2n minus 1 when k equals n1. So add the 1, so that is going to be 2n, right? And that's a bit 2n. And what is m? M is going to be the derivative of the 2n plus 2n's order. So here, if the derivative of 2n x less than or equal to n, okay, for x less than or equal to d, okay, remember that. But you can always make m to be 1 because the derivative here we already find out it's going to be negative 1 to the power n sine x. So this can be noted that this can be negative to the n sine x. It's always equal, less than equal, f for any d, f for any x. Okay. So using this, we can have the following estimate. It's always equal to 1 over 2n factorial and x to the 2n. Okay, and no matter which x you choose, yeah, here's x is less than or equal to d, but these are arbitrary, right? So clearly, when n goes to 0, it's going to be 0. This side is going to be 0, approaches 0, as n approaches infinity. Okay? So that means sine x is always equal to for any x. So we find now we find this we find our k starts from 1. Sorry, I always, when k equals 0, then that will be negative. Yeah. Okay. Yeah. So we get this, but you can also rewrite it again when you can rewrite the let k. You can use a new index. For example, I equals k minus 1. So I will be starting from 0 to infinity. And then 2k minus 1 will be 2I plus 1. Right? And here will be I. Here will be x to the 2I plus 1. That's another one. Okay. All right, so this is a sine x. We do get the formula. Okay. And here's I equals k minus 1. Okay. It's very similar to the exponential function. It's similar to the e to the x. Okay. All right, so now how to get a cosine? Should you repeat again? No. Just differentiate, right? Differentiate both sides, because this holds for any x. Okay, so radius convergence is going to be infinity, so don't worry about that. It's just differentiate. If you differentiate, you get cosine x. Right, and it cancels out. To I factor here in negative. All right, so you get another one. Quickly get the Taylor series form. Get power series representation for cosine x. Okay, so let's look at the first few terms. Let's look at the first few terms. For sine x, when I equals 0, I get x minus when I equals 1, 3 factorial, right, negative, and x cubed. Okay, the fourth term is going to be when I equals 2, it's a 5 factorial x to the fifth, then minus 7 factorial x to the 7th. So that is the first few terms. Okay, so you can using polynomials to approximate sine x. So that's the power of the power series. Okay, you can always use polynomials, high order polynomials to approximate sine x. Okay, if you use, you can do a test. So you write down this polynomial for up to 100 terms. So more terms and more accurate. Then you draw the graph for this polynomial, okay? And you find out almost looks like a sine curve, okay? For x close to 0, right? If you choose 100 terms, then probably you can make a very large interval. So on that interval, the difference between sine x and that and this polynomial is very, very small. Okay. So similarly, cosine x, the first term is 1. Yeah, because cosine 0 is 1. The second term is going to be 2 factorial x squared, then plus x to the fourth, 4 factorial, and minus x to the 6, 6 factorial, and so on. Okay. All right, so my next question is, find the power series representation for sine x at x equals pi over 2. All right, so that means I'm going to try to get something like that, x minus pi over 2 to the x power. So how do you determine coefficient? What is the best way to do? Well, you can repeat it, right? What I did for sine x, you find all the partial derivatives, all the derivatives, and evaluate at pi over 2, right? You can try. We can try this one, right? And then the problem is that when it takes much longer time to solve the problem. When you finish the problem, you probably only half hour left. Okay, you don't have time for the exam. Okay. Yeah. So we have to do like the other problems, modify the function. Okay, sine. You see, I want to expand, right? So you let u to be x minus pi over 2, right? Then x is going to be u plus pi over 2. Okay. So sine x is going to be sine u plus pi over 2. Got it? So I'm going to write the power series. I'm going to express it in this form, Cn and u to the power n, because u is x minus power 2, right? So all I have to do is to find a way to get that. But we know that this is going to be sine u cosine pi over 2 plus cosine u sine pi over 2, right? Yeah, cosine pi over 2 is 0. So actually it's nothing. This is just equal to cosine u. Okay, and I already know that cosine u, right, is going to be, cosine x, right? So it's going to be n start from 0, it's 2n factorial, and the u to the 2n. okay, for all x. So that is going to be, and here's x minus power 2 to the 2. That no restriction on x because this holds. Okay. That's for all x. Okay. So similarly, you can do the next one. Let me ask you to do that one. Find the power series representation for f of x, which is cosine x at x equals pi over 3. How about that? Okay. Yeah, think about how to do that. It should be, you can do a similar way, right? Okay. So the idea is very similar. We practice for that. So you let u to be x minus pi over 3. Then x is going to be u plus pi over 3, right? Right. So cosine x is going to be cosine u plus pi over 3. The question is, do you still remember the formula to expand this? Okay, it's going to be cosine u cosine pi over 3. I think it's minus. That's the problem here. Okay, subtraction. All right, so cosine pi over 3 is going to be 1/2. And sine pi over 3 is going to be square root 3 over 2 sine. Then, since you already know those two power series representation, the first one will be cosine u, and starts from 0, negative 2n factorial x to the 2n. Okay, the next one will be for the sine. Sine can be written in the form 2n plus 1. Okay. And this holds for all x. So you can also write and put them together. It's a little bit difficult to describe it. Because here's the no common term, x to 2n, x to 2n plus 1. Okay. So you can write in the following way: k equals 0, ck, and x to the power k, right? But then you have to decide what is with this ck. Okay, and when k equals 2n, when k equals 2n, and this is going to be negative when k equals 2n plus 1. You can describe it in the form. The coefficient is defined by this formula. Okay. Sorry, this is a u, not a confused. This is not a x. Okay, this is a x minus pi over 3, so it's u. Okay, and the way you just say that u equals pi x minus pi over 3. So you get power series representation at pi over 3. Only the coefficients are a little bit complicated. It depends on when the k is even, when k is odd. So now my next topic is trying to focus on the function f of x equals equals 1 plus x. I'm going to use alpha, okay? Because it's not as alpha, it can be any number, okay? This could be any real number. If I use k, looks like an integer, okay? So any real number, alpha could be square root of 2, square root of 3. And let's try to find the telex, trying to find power series representation for this. Okay? I know this can be defined. And f is differentiable for any x greater than equal to -1. So okay, this is differentiable many times, as many as you want, on the interval. This is defined on the interval from -1 to positive infinity. All right, so I'm going to find the power series representation at x equals 0. Right? In other words, this should be equal to something like that. Okay, and the largest radius convergence we expect is 1, right? Because it's from negative to positive infinity. So this function is not defined when x equals -1. So with radius, the convergence equal 1. Maybe. Okay, let's try. That's the best that we can hope. Okay. We have to find the derivative. So derivative is not complicated. It's not easy. It's not difficult to find out. Okay. The only candidate is the Taylor series. Okay. The only candidate is the so-called Taylor series. Okay, which is given by this. Okay. You have to write down Taylor series, but then you have to still have to prove it is convergent to the function on the interval from negative to positive. But let's find this candidate first. Candidate is very important to find a candidate. No candidate cannot have an election. Right? Yeah. Is that could happen someday? No candidate. So there should be some kind of a rule there, right? If suppose there was no candidate, the current president should be continued. Right? Nobody win, you know. Right, so this is a candidate. Let's find the partial derivative. It's not easy to find the formula for the nth order of the derivative. Okay, but this one, yeah, we can find the pattern. So f of x equals 1 plus x to the alpha. Then I differentiate. What I get is alpha 1 plus x to the alpha minus 1, and it continues. Okay. I have to, sometimes I have to stop, you not continue. You're going to get 0. If alpha is some positive integer, you will stop somewhere. Otherwise, it continue forever. Okay. So f of n, x is in alpha, alpha minus 1, and alpha minus 2, and so on, alpha minus n minus 1, and x to alpha minus n. Okay. You don't need it to continue if alpha equals some n. Okay. Then the derivative constant is going to be 0. Okay. Otherwise, just continue, differentiate, but then the coefficient contains 0, so it's actually is always 0. Now this number, right? I'm going to introduce notation here. So oh, 1 plus x. Okay. So you can evaluate 0. You get it. Okay. So now you get n factorial f of n, right? It's going to be this coefficient. I'm going to use another notation for that. This is denoted by alpha n. Okay. Yeah. So then you get this. We still have a question whether or not this is convergent to the function. Okay, we can prove that. Okay, it's convergent function. Okay, so claim f of x 1 plus x to the alpha is going to be this for x less than 1. Okay. So you do have this formula. The argument is very similar. The only problem is the argument is very similar. What? Where's my what? Okay. The argument is very similar. I am not sure I should prove it. Okay. So just do some estimate. Okay. So the idea is you look at the ends, for x less than equal to d, d is less than 1, okay, for arbitrary d. Where is arbitrary? And then f of n plus 1 x, okay? This is going to be, this is going to be absolute value of that. It's going to be alpha minus 1, alpha minus n plus 1. and this is going to be less than or equal to but which is smaller than what? Okay, and so the error okay, so the error here equals to the k, okay, is going to be smaller than, I think this is not n, this is not n minus 1, so n. Yeah. Wait a minute. This is a bit alpha minus that. Alpha minus this. Yeah, I'm going to the derivative. Hold on. This is there was a mistake here. Okay, so you have to have a 1 plus x to the n plus 1. The question is how do you estimate this? Okay, this is a alpha minus this. For sufficient large n, this is going to be negative. So it's in the denominator. Okay. So I believe that this is going to 1 minus d to the alpha n plus 1. Okay. Yeah. It's in the denominator. So this is the largest value. Okay, so 1 minus d to the alpha minus n plus 1. And you also have x to the n plus 1. Okay. So all you have to do is to prove this is convergent to 0. Okay. It's convergent to 0. Well, that's tough. I don't want to waste it. So this, yeah, this you have to prove that this convergent to 0 as n approaching infinity. Okay, and for x less than, yeah, x is less than or equal to b. These are fixed. Yeah, so we're not going to check this. We just take a look at an example. For example, f of x is going to be square root of x. Okay, let's find the process representation for this. I think it's easy to prove that for x less than equal to for this is x less than equal to d, but if the d is less than equal to 1/2, it's easy. Otherwise, no, the book does not give a proof. Otherwise, it's much more difficult to argue. Okay, so we're not going to use that. So let's just find the process representation for this function using the above formula. So here, alpha equals to 1/2. Okay, so the power series. So this is going to be, it's going to be alpha 1/2 n x to the n. Okay, and this is for x less than 1. So the coefficient depends. It's going to be n factorial 1/2, 1/2 minus 1, 1/2 minus 2, and 1/2 minus n minus 1. So those are the coefficients. We cannot simplify. Okay, we can only estimate. We cannot simplify further. Okay, so the first few terms. Let's look at the first few terms. Okay, when the first few terms, that's still 1. Okay, and that is going to be that is going to be 1/2 over 1 factorial is 1/2. The third one is 2 factorial here is 1/2, 1/2 minus 1. So it's going to be negative 1/4 divided by 2, negative 1. It's very sufficient, very small number. 3 factorial, 1/2, 1/2 minus 1, 1/2 minus 2. So let's figure out what is on top. The bottom part is 2 times 3. The top part is 2 cubed. 1 times negative, okay, negative 1, and 1 minus negative 3, okay? So it's become positive. 3 cancelled out. It's positive half, positive 16. So it's interesting to see that it's going to be 1 minus, it's plus, yeah. Okay, so the next one will be negative. So it's kind of alternating series except for first term. So this is what we get. Okay, we can have few terms. The square of 1 plus x can be approximated by polynomials. The coefficients. Okay, you can write down the first few coefficients. Okay. So very last, yeah, let's try to find this. Find the power series representation for the function cosine x. Okay. Wow, cosine square x. This is going to be at a equals 0. Okay, so you not only find it's called the Maclaurin series in this case. You not only find the series, you have to prove they're equal, right? So how do you solve this problem? Right. I only know this one, right? I only know the power series representation for cosine x. Cosine x. Let me write down this. Can I use that or not? Right? This is a holds for all x, but there's x squared there. Can I just square the power series? No, that's not a good idea. So just like an integral, cosine square x can be changed to cosine x. Okay, so cosine square x is going to be 1 plus cosine 2x divided by 2. That's all we need. Right? Okay. So it is going to be 1/2 plus 1/2 cosine 2x. Then I apply the above formula. And 2x to the power 2n. Done. Yeah, modify a little bit. Right, this is the coefficient. Okay. I think that's except for the first term, when n equals 0, and you get to 1. Otherwise, you can n start from 1 to infinity. So I get 2n factorial negative n and 2 to the n minus 1 and x to the 2n. Okay? So yeah, this will be just a 1. Yeah, this combines 2 just a 1. And that's it. This is power series representation. It's hold for all x. All right, so next question. Let me repeat the definition. I mentioned several times, I did not say that. Right? Given f of x. Right. This series, you can differentiate many times in one. This series is called the Taylor series. At A. Okay. So if I ask you to find the Taylor series, you have two options. One is use a formula, definition, to find Taylor series. Another one is, the fact is here, here's the important fact. If f of x is going to be okay for x minus a less than r is positive. If you know already that, then this is a Taylor series. Okay, then all the coefficient number is this, i.e. this power series is a Taylor series of f at a. Okay, so that means you can use a power series already more defined function. Use the already known result to find the powers to find the Taylor series. Okay, for example, this one. Find the Taylor series for the function e to the x squared at 0. That means you have to find this, right? I don't need to prove this equal to the function. But when you're trying to find the derivative, it's harder to find the general formula. Okay, when you differentiate, look at that. So don't be hurried to solve the problem immediately, right? Look, you remember the definition. Okay, I'm going to find the derivative. Okay, fine, derivative. The first derivative is easy, e to the x, then 2x. And then the second derivative, e to the x squared. Or the product was 2 plus e to the x squared, then 2x squared. And then you get more terms, it's harder to find. The general formula, okay? More complicated, okay? I think it's not easy to figure out. Okay. And if you want to look at the third derivative, e to the x squared, then 2 here, and 2x, right? Yeah, then you find that e to the x squared, and 2x is 2x cubed. Then you have e to the x squared. Oh gosh, right? So 2x times 2. So it's really difficult. Okay, it's harder to find a pattern. It is hard to find the formula for this. All right, and it's order. So I'm not going to use this definition to find the Taylor series. I'm going to just go ahead and find the power series representation. If I find the power series representation, that's it. That's just Taylor series according to this theorem. Okay. Right. This theorem says that if the function you already know the power series representation, and the coefficients must begin by this formula, then this is by definition this is a Taylor series, the power series. Okay. So e to the x, I know e to the x is going to be n factorial x to the power n. So e to the x squared, very simple. Just replace x by x squared. Right? That's it. So this is the Taylor series. Okay. Yeah. This is the Taylor series of e to the x squared at a equals 0. And it is also called the Maclaurin series. Because Maclaurin, I think, did the first some partial work, just only focus on the power series representation at the origin. Okay? Probably they're independent. Because early days, the information that cannot exchange so quickly, right? You know that 200 years ago. Yeah, it's not like these days, you can talk to your mom in California without any delay of seconds. You can even see the videos. And in the future, the technology is better. If you really love your parents, you take a 3D video, record it. So every time you want to see them in 30 years, you just play back there in the living room. You're scared, right? That's okay. The technology is already there. Some kids that don't need to go to a field trip to Zoom. They just sit inside campus, inside the the lecture hall or something, playground, and they play the video, the 3D video. The kids all sit there, and the giant dinosaur came out, walking out. They go, whoa! You even see the dinosaur, right? So you don't need to go outside. It's the same story here. Okay. Yeah, that's the future. Okay. And it can become You don't need to make the real person. You can make the fake when you can talk to him even, because that's programmed. He understands what you're thinking. He tried to talk to you, release. Sometimes people get depression, and they just put a video there, and they can talk to you. Okay, so this it's great future. We can see that, and you don't need a cell phone in the future. I'm pretty sure. I can live to the day there's no cell phone. The piece of you hold on in your hands. Okay. All right, so we stop here. We're going to have a review class, okay? Then we're done.